hide your video or something like that. Okay, so we're going to start with two-dimensional vectors, and then we might get into 3D a little bit today. If not, we'll for sure get into the next class meeting, okay? So here's the deal, folks. I'm not going to do any calculus for like the first week or two of this class. So when you go home tonight, and mom will go, hey, how was calculus? And you'll go, we didn't do any. And your mom will go, hey, what am I paying for there? And the reason why is because we need to lay down some foundations here in Calculus 3 for you. And that is vectors, because they're going to be very important for the entire class. Now, if you've taken physics already, you may have a little bit of knowledge of vectors. It may be enough, but probably not. So I'm going to do a whole bunch of stuff with vectors, fun and play with vectors, and then we'll get into the calculus. So keep that in mind while we're doing this vector stuff, and you may be thinking, what does this have to do with calculus? We'll get there, but then we'll bring vectors into the conversation when we start our calculus. So one other thing I do want to say, if I were to synopsize this class in 25 words or less, a very simplistic view of what we're going to be doing here in Calculus 3, it is the following. You are basically going to do Calculus 1 all over again, except you're going to do it in 3D. So may I remind you that when you took a Calc 1 course, there were two things, basic things that you did in that class. There was a lot more than that, but we'll start with just the two basic things you should have learned in Calc 1. One thing was, if you were given the graph, say, of a function y equals f of x, you remember in Calc 1, they would ask you, hey, here's a point, and there's a tangent line to the point. Give me the equation of the tangent line to that point. Do you all remember that?
Yes.
That was because you had to go find the derivative. Because the derivative gave you the slope of the tangent line, and then you use your knowledge of algebra to get the equation of the tangent line. So that was one thing that you did in Calc 1. And a second thing that you did in Calc 1 was same graph of the same function. They would ask you to find the area under the curve. Remember that? And you had to go get the integral because area was the integral. So hopefully you remember how to integrate, and that's important because you're going to do a lot of it in this class. So over here, the slope was f prime of x to this line. So what are you doing here in Calc 3? Well, in Calc 3, you're going to do everything in 3D. We'll do some things in 2D also. In fact, we'll start with 2D. But the first thing you're going to do here in 3D is you'll have some surface. I'll call it a capping surface. And I'll pick a point here on the surface. And I'm going to want to know the slope at that point on the surface. And you can kind of think of this surface as maybe being a mountaintop. And you're going to ski, right? This is you sitting on the mountain, and you're going to ski in a certain direction. You want to know the slope. And so we're going to learn how to do slopes in 3D. And similarly, underneath that capping surface, if I were to create a solid, I'd want to find the volume of this solid that has this capping surface to it. So you're going to be finding volume instead of area, and we'll be using either double or triple integrals in order to do that. Don't worry yet, we're not going to do double and triple integrals till October, but I'm setting up for what this class is basically going to be doing. And there's even more fun and good news. Hey, you guys remember sequences and series from Calculus 2?
Oh,
Yeah.
We're not going to do any of that in this class.
Wait, what?
yes.
Thank God. Thank God.
None. No sequences, no series. Aren't you happy?
Yay.
Yay! Now, for those of you who are like, well, I hope I never see that crap again, let me just warn you that if you have to take differential equations, also known as Math 253 here at Southwestern College, you will have to do a lot of stuff with series, okay? So don't completely forget it if you still have to take differential equations. But we don't have any in this class, so that's good news. All right.
Please don't take DiffyQ over the summer. It was a mistake.
Wait, you did that?
Yikes.
Along with Physics 1, it wasn't great.
What was your grade?
All right.
I got B's in both through some fucking like act of God.
Oh my
David.
God.
Keep your language. Remember, I'm recording.
Oh, oopsie.
This is
Frick.
going to be recorded for next
This isn't
semester's
Calc 2,
Calc 3 class.
Frick.
Ooh.
Okay, let's do some definitions. And then we'll get to some actual problems, and then I'll have you maybe try a couple problems. How about that? Better stay awake, otherwise you won't be able to do it. Okay, what's a scalar and what's a vector? A scalar, I don't know, you scale? No, you don't scale anything. A scalar is a quantity that can be characterized by a single real number. It's just a pure number, like the number 2 is a scalar. Okay, fine. So what are some examples of scalars in real life? Glad you asked. Length is considered a scalar, like the length of a table. Area is considered a scalar. Volume is considered a scalar, and there's many more. Those are some 3 easy examples. What about vectors? What of it? Well, we're going to study a lot about vectors this week and next. So a vector isn't a scalar. It's a quantity that has 2 properties associated with it. It's got something called a magnitude, which is essentially its length. But if you're studying vectors in 4 dimensions or 5 dimensions or 6 dimensions, which we're not going to do, then your magnitude isn't really considered a length, but you still can talk about magnitude in any dimension. If you're taking linear algebra, which is Math 254, you'll be doing vectors in that class also, but you'll be doing all sorts of dimensions, 2D, 3D, 4D, it's fun. That class is great. The other thing that you have to worry about when you're working with a vector is the direction, like which way it's pointing. So some examples of vectors in real life, and these have a lot of physics properties. Force is a vector. And what are some forces? Well, velocity is considered a force, so you need a vector to show it, and acceleration is also. These are some examples of forces, vectors. Okay, let's look at a picture of a vector. Here's a picture of a vector, folks. So what is that picture? Well, mathematicians call it a directed line segment. So it's a line segment that has a direction. And you know what direction it's pointing because you got a little arrow on there. So a vector is a line with an arrow attached to it. So let's label which one of these points, A or B, is considered the tail and which one's considered the tip. Okay? So I'll throw it out there. Does anybody know which one of these points, A or B, is the tail? I don't expect you to know, but
It's A, right? Yeah.
A is the tail.
yeah, the tail is A right there. Okay, right there, that point right there is considered the tail. And this point that's at the very tippy top of the arrow is considered the tip. Okay, now some other things that I'd like to label here because you need to know, and you even need to know it on the midterms and the final. This is important, people, so hopefully you're awake. I know, I want to go back to bed too. Which one of these points, A or B, is the initial point? Which one is the terminal point? And it turns out that A is the initial point, and B is considered the terminal point. And you need to know this vocabulary, because if you don't, all the rest of your quizzes and exams, you'll be hurting. Let's look at some notation for denoting vectors. When you're denoting a vector by its initial and terminal points, you'll use usually capital letters naming the points A, B, and you'll see a little picture of an arrow over the top. So if I were to do this by hand, I'd probably do it like that. Order matters. The vector AB is very different from the vector BA. The vector BA would be the same length, but it would be pointing in the opposite direction. Okay? So textbooks refer to vectors in boldface, and they typically don't use this AB type notation. They'll use this. This is textbooks. They typically use lowercase letters, and they do it in bold. And we're not going to do that when we do handwriting. So in handwritten, the way I want you to do it is when you write down on a quiz or an exam, you'll just put V and you'll put a little vector on top. You could do it like this also. I'm okay with that also. Either way, I'm cool. So that's how you're going to denote a vector from now on in this class. Okay, key weird fact. that you need to know. Every time you look at a vector or somebody is telling you about a vector like V or AB, that single vector actually represents a set of vectors, infinity vectors. What? Yeah, that one vector represents every other vector in the whole universe that has that particular direction, pointing in that direction, and having that same magnitude or length. So remember that, because it's going to come in handy when we do lots of problems. Okay, now let's talk about the standard position of a vector. And I'll stop for questions soon, so I just want to get through a lot of these administrative definitions about vectors before we get to something we can do business with. When you have a vector in standard position, it means that the initial point, that's key right there, the initial point is located at the origin if you're using the rectangular coordinate system. So knowing that, we'll get to a picture in a moment. If a vector V is in standard position, that means its initial point is stuck at the origin, then you can write the vector in a very nice way. You can write it using these angular brackets and then a number, comma, a number, where V1 and V2, those are going to be scalars. Those are also referred to as the scalar components of V. Fill in the blank. Scalar components of V. And this form of the vector is known as component form. If you've taken physics, you're probably not as familiar with the component form as you are with the IJ format, which we will get to. That's not my personal favorite, but we'll get to that soon also. Okay? The zero vector. What about the zero vector? The zero vector is denoted with a 0 with a little vector on top. That's to distinguish it from the number or scalar 0, which is different. If you are showing the two-dimensional component form of a zero vector, you're going to use those angular brackets, and 0, 0 would be the scalar components. If you were to draw the zero vector, it actually just looks like a dot because its magnitude is 0. And its direction, or where it's pointing, is everywhere. Well, how is that possible? Well, because the dot doesn't really have an arrow, you think of the zero vector as pointing everywhere. I know. I don't make this stuff up. Don't shoot the messenger. I'm just reporting it. Okay, now let's look at how to find magnitude once you're given the components of a vector. If you're given a vector in component form, to find the length, which is denoted with double bars around the vector's name, or Briggs, our textbook, uses single bars, which I'm never going to use on my lectures or my exams because it looks too much like absolute value. But other textbooks use that too, but better textbooks use double bars. You're going to be just using this formula to find your magnitude. This is the formula for a 2D vector. You just take the sum of the squares of the components and then take the square root of that. Okay, now let's talk about the difference between a geometric vector and an algebraic vector. And then we'll actually do a problem, and then I'm going to have you try one. Okay, so hopefully you're staying with me here. I know there's a lot of definitions and things like that. But if you drew velocity on my force diagram, okay, yeah, well, you can. Okay, so let's talk about looking and drawing vectors. Okay, suppose you're given an initial point, we'll call it P, and let's say the terminal point is Q. So you just have P and Q out there somewhere in space. How do you create the vector PQ, which would look like that? You have to do it where the x scalar of your PQ vector is the difference of the x coordinates of your points, and order matters. So you have to go terminal minus initial, x2 minus x1. And then the y scalar component of your vector is the difference of the y coordinates of those 2 points, y2 minus y1. Make sure you don't do it backwards. It's always terminal minus initial, and that's going to be your key to doing this. All right, so here's an actual example I'm going to do. Take a look here. They're giving us 2 points in 2D. And we're going to come up with a component form of the vector AB, and we're going to sketch the geometric and algebraic vectors, and we'll also give the magnitude. Not necessarily in the order shown here. In fact, I'm going to do part C first, if you don't mind. Let's do part C. How do you draw the geometric version of this vector? Very easy. You just plot the points and connect the dots, and make sure you put the arrow at the terminal point. So if we're supposed to form the vector AB, then let's take a look here. The point A, which has coordinates 8, -3, so I'm just going to locate here the point 8, -3. That's A. And then the point 4, 5, let's see, 4 is here, 5 is way up here, so the point 4, 5 is right there. There's B. And then the vector AB is going to look like this. That's it. That's the geometric vector. The book does not talk about geometric vectors, but when I taught trigonometry, they distinguish between geometric and algebraic, and I think it's important. Now, what's the algebraic version of this vector? Remember, this vector is representing infinity vectors, all of them who are pointing in that same direction and who have that same magnitude or length. So the vector, the algebraic one, we're going to get that next. So how do you get the algebraic one? You're going to go terminal minus initial, terminal minus initial. So if you look at, oh, I'm saying PQ. Sorry, I should say AB. My bad. This vector is named AB because of the points. So you're going to go 4, that's the terminal x coordinate, minus the initial x coordinate, 8. That is going to be the x scalar component of this vector AB. And now let's get the y component. You'll take the y coordinate of B and you'll subtract the y coordinate of the point A. And now let's do a little bit of arithmetic here. The component form for this vector is -4, and 5 minus -3 is 8. So this is the answer for part A. There is the answer for part A. That is the component form of this vector. Now I'm going to use the component form of the vector to help me draw the algebraic version of the vector. So now I'm going to draw the algebraic vector. What is the algebraic vector? It's the vector in standard position. So in standard position, the initial point is automatically by default located at the origin. We just have to find the terminal point. So the terminal point can be found by just graphing the point given by the scalar components of this vector. So just find the point -4, 8. So there's -4, and then 8 is up here, so it's like right up here. Oh, I'm not being, let's see here. My pen is starting to get too hot. There it is. So that point right there is the terminal point, and so the vector that is the algebraic version of the same vector AB looks like that. So this terminal point has coordinates -4, 8. And I'm using parentheses to denote a point, but I use angular brackets when I'm denoting the vector. Please get this straight, because on an exam, even if everything else is perfect on your exam, but your notation is off, I will take away a point or two. So it does matter. Okay? So there's only one more thing for me to do with this example, and then I'll take a quick break and take questions. I've already done part A. The answer is right here. I already drew pictures. I've got the geometric and the algebraic version of the vector, so I've done part C. I haven't done part B yet. So part B is saying, what is the magnitude of this vector AB? So the magnitude, which I like to denote with double bars, is simply using the formula above, the square root of the sum of the squares of the components of this vector, where the components are, which we got when we got the component form, -4 and 8. And then do a little bit of arithmetic here. What the heck here? -4 squared is 16, and 8 squared is 64. and then you're going to take the square root of that sum, and I get, square root of 80. And I like you to give me exact answers, so please don't whip out a calculator and give me the decimal result here. I'll mark you off. I want to see, sometimes my math lab might ask for it, but typically they want exact answers. I do want you to simplify completely your radicals. So hopefully you remember that 80 is factored as 16 times 5, and 16 is a perfect square. So when you simplify, the magnitude here is 4 square root of 5. And that is a scalar because it's a pure number. So a really important point when you're comparing two vectors with each other is to see if they're equal or not. Now, of course, the obvious way to see if they're equal is to just draw a diagram of both vectors, and if they both have the same exact length and they're both pointing in exactly the same direction, they're equal. But we don't have time to waste drawing every single vector in the universe this semester, so you want a much quicker way to do that. So the much quicker way to do that is simply to get each vector that you're trying to compare to see if they're equal or not in component form, and then just checking to see if there's a match between the scalar components. So you just want the x component, u1 has to equal v1, and you want the other scalar component, the y component, u2 to equal v2. And if both are a match, those vectors are equal, and then you don't have to check direction or length or anything like that. You're done. They're equal. Okay, let's look at some fun and play with vectors, and we'll fill in the blanks while we're doing it. I could have just handed this to you, but the process of writing and filling in the rest of it will hopefully enforce it for you a little bit more, especially if you haven't had your morning coffee yet. So wake up. So let's start with two vectors in the plane. And let's do, we need to talk about what is the plane. Is this a jet plane that I'm talking about? Anytime you hear the word plane in this course, it will not refer to an airplane. It will mean 2 dimensions. So anytime you hear, oh, this vector is in the plane, or this curve is in the plane, it'll mean restrict yourself to 2D. Because we are going to be doing the same things in 3D as well, and there will be a slightly different flavor and a different name too. We'll get to it. Now, C is going to be a scalar. So what does that mean? It's just a pure number. So if you are trying to add two vectors together, which is totally allowed, and our physics brethren do this all the time, they're going to go, hey, here's u, here's v. What's the sum, u plus v? Well, good news, the sum is also a vector. And the way you add the two vectors together to get one big old vector, that vector result, the scalar component for its x is simply going to be the sum of the x components that you see for those composite scalars or composite vectors and comma, and then you simply add the y components together to get the overall y component for the resultant vector. And we're done. What about scalar multiplication? So let's say you're trying to take a pure number like 2 and multiply it with your vector v. And you might, the intermediate step kind of looks like that. Very easy to do this. You can kind of think of distributing the scalar over the components. So it's going to be whatever that scalar is, like the number 2 or -2, multiplied by the first component, comma, and then that same scalar multiplied by the other component. And we're done. Well, that's really easy. Is it really that easy? Yep. Okay, what about the negative or opposite of a vector, which you'll denote negative v? It's the same as essentially multiplying your vector by a scalar of -1, and you'll just distribute that -1 over the vector again, so you'll get negative v1 as the first component, comma, negative v2 is your second component. That easy. Now let's talk about this real quick, visually speaking. When you negate a vector, the magnitude is still maintained. It'll have the same length, except it'll flip over and point in the exact opposite direction. In essentially 180 degree, it'll make a 180 and point in the exact opposite direction. That's important for you to know, because you'll be asked that on tests and quizzes all the time. What about if you take the difference between two vectors? So u minus v. No problem. You'll get one big old vector result, and you'll simply take the difference of the x components to get the x component for this result, comma, and then take the difference of the y components, and you're done. Okay, now let's talk about what it looks like to add or subtract vectors visually speaking with the eyeballs. And if you've taken physics, hopefully you've seen this before, but if not, it's important. I'm going to give you both ways because some of you are going to go on and take a course called vector calculus, and you'll be asked to prove these ways. What's vector calculus? We're going to be doing some vector calculus at the very last part of the semester, like your last month. But if you go to UCSD or San Diego State and your major requires the next, and usually all engineers at UCSD have to take the next one, which is vector calculus. And so it's important to know these two ways of looking at vector addition. Way number one, it's called the tail to tip method. So let's just say you started with some vector u and some other vector v out here. And this could be in 2D, 3D, or even 4D, you know, whatever, although we can't picture 4D. So the tail to tip method works like this, okay? I'm going to just copy down the u vector here. And I'm going to translate the v vector, or move him. I still have to maintain his integrity, his length and his direction. And I'm going to move him so that his tail is touching the tip of the u vector. And so there, I just moved the v vector over. And then the sum of u plus v is where I start here at the tail of u and end up at the tip of v. So this blue vector here is the resultant vector of u plus v. And it's important that you get that because we do a lot of summing with vectors. So that is called the tail to tip method. It's also known, AKA, means also known as the triangle method. So some books refer to this as the triangle method. Can you think of one reason why they refer to this as the triangle method? Go ahead, somebody throw it out.
Because they're squares.
Well, what does this diagram look like to you?
Mhm.
Half a square.
It's a triangle. I would say it's more like half of a parallelogram because the squares, you usually want your sides to be straight up and down. So some books will refer to this as the triangle method. Now I'm going to go the other way, and this is more common. And if you take a vector calculus class, they'll probably make you do some proofs with this one. So once again, let's start with u and v where they were initially. Let's say u is here and v is way the heck over here. And somebody says, okay, add those vectors together, but use the parallelogram law method. Okay, how do we do that? What I do is I'm just going to copy down u again, and I'm going to translate v again. But this time when I translate v, I'm going to put him where both of the tails are touching. Now this part is going to require a little bit of your imagination in order for you to picture this parallelogram method. Can you imagine that these adjacent vectors are two sides of a parallelogram? Adjacent sides? So if I draw the other two sides of the parallelogram, I'm not too good at drawing, but that was terrible. Sorry. Whoops. Let me get that back down there again. Whew, do I have a lag or what? Okay, so I've got my other side length there. The resultant vector is the diagonal of this parallelogram. So this u plus v is simply the diagonal of the parallelogram, this imaginary parallelogram, okay? And that's the parallelogram law. Okay, now what about vector subtraction? Well, what of it? What is the resultant vector looking like if you're taking the difference between two vectors? Well, let's say once again you've got u and you got v over here, and somebody says, well, I want u minus v. So the way to do it is if you touch their tails together again, the u minus v is going to simply be where you connect their tips together. I know. So you're just going to go u minus v, and by the way, order matters. U minus v is this red vector here. And if you connected it in the opposite direction, that would be v minus u. Uh-oh. I now know why my... Watch this, right? Perfect, thanks. Okay, so vector subtraction, you can change it into adding a negative and use the parallelogram law. And scalar multiplication, you can think of it as stretching or shrinking your vector. You either stretch it out or shrink it, and if you multiply by a negative, that means you point in the opposite direction. So these are all the little visuals that you can use to help yourself when you're working with vectors. I'm not going to have you draw a whole bunch of vectors, but it's certainly helpful to see them so you get a better idea, okay? So now what I want to do is I want you guys to buddy up with somebody. In fact, I'm going to put you in breakout rooms, and you're going to do example 2, A, B, and C right now. So to tee it up, somebody is giving you the component form of u. His components are -3, -8. And they're giving you another vector v whose components are 8 and 25. And you're going to form some brand new vectors using your knowledge of scalar multiplication and vector addition and subtraction. I'll give you one hint. Just like PEMDAS in an algebra class, you want to do the scalar multiplication before you would do any addition or subtraction, because that's more important, and that in the hierarchy of order of operations, that should come first. So you don't have to draw any pictures here at all, which is kind of good. So I'm going to pause the recording again, because I can, except I can't see my cursor. There we go. Okay.
There you go.
Okay, can you guys hear me and see me okay?
Yes.
Welcome back. Was that beneficial to you?
Yep.
Yes, it was.
Good. So let's just go over some of these in turn. When you do scalar multiplication, I hope you remember you just distribute. And then, of course, you want to reduce to lowest terms. So 2/3 multiplied by -3 reduces to -2, yes?
Yes.
And then 2/3 multiplied with -8, well, you know, it's -16/3. So that's the answer I should have seen for part A.
Yep.
For part B, when I went to some of the breakout rooms, because I was visiting some folks, some of you accidentally read that backwards, but it's V minus U, not U minus V. So you have to be careful, because they're saying, what is 825 minus the U, which is the components of -3, -8. And order matters when you're doing subtraction. Adding, nobody cares. Subtracting, we do care. So here, your X component will be 8 minus a -3, and then your Y component will be 25 minus a -8. You got to be careful here with the arithmetic. And then 1133 in component form is your final result. And then finally, letter C involves both scalar multiplication and addition. And so you want to do the scalar multiplying first, of course, which is involving the distributing, if you will, first. So you're going to really add the vector -6, -16 to the vector 40, 125, and then you're just going to add the components. So -6 plus 40, I believe, is 34, and then -16 added to 125 is 109. Did anybody get this?
Yeah.
Okay, cool.
Yes.
Now, I never finish class on time. I'm going to probably almost always go all the way to 10 a.m. So if you have to bail out early because you have to whatever, that's fine. I'm okay with that. But then watch the recording so you can get the notes, okay? So I'm going to keep going here. 15 more minutes. We're going kind of slow, believe it or not, because we spent a lot of time with the administrative stuff at the beginning of class. Letter D is very important, and it's kind of hard. And yes, it's going to be on the quiz Sunday. Which is due Monday morning. You have a 24-hour period to complete it. But it's 90 minutes. But I'm opening it up on Sunday morning. So this is a linear algebra type problem, and it's really important that you know how to do it. So what is it? and if you when I first read it to you, you're going to poop your pants, okay? Suppose W is this vector, 14, 41. Okay, what's the big deal? Find scalars A and B such that W can be written as a linear combination of the vectors U and V. Now, who's U and V? U and V are still these guys given to you at the beginning of the problem. So you already have been doing some other stuff with those two vectors. But you're trying to write W as a linear combo of the other two vectors. This is something that we do all the time in linear algebra, Math 254. And again, it's going to be on quiz 1. And after you do the setup, you're basically going to end up with a linear system of equations, which you learned how to solve in a baby algebra class. So it's a lot of stuff there, algebra with vectors. Me likey. Here we go. So what are they asking us to do? We want to write W, which looks like 1441, as some number A times the first vector U, which has components -3, -8, plus some other scalar B, who the heck knows what that guy is, that's what we're trying to find out, times the other vector with components 8 and 25. Okay, so what I'm going to do here is I'm going to use our knowledge of scalar multiplication and vector addition, and then we're going to use equality of vectors. Do you guys remember that way back here? I said it's really important. You should know it. This is going to come into the conversation, people. You may have thought, oh, that's really stupid, equality of vectors, who needs that? Well, that is going to bail you out on multiple occasions in this class, and this is one of them. So what we're saying here is this vector W is going to be equal to the sum of the vector -3a, -8a, plus the vector 8b, 25b. And now I'm going to add these two together using our knowledge of vector addition. So we'll get one big old vector where the x component is the sum of 3a and 8b, and the y component is -8a plus 25b. And now the equality of vectors is going to come and save us. Why? The left-hand side vector has to be equal to the right-hand side vector. Yeah, so what? That means the components must match. We need 3a plus 8b to exactly be equal to 14. And further, we need -8a plus 25b to equal 41. And this, folks, is a linear system of equations that you learned how to solve from an algebra class. Well, how do we do that? Well, you know, there's multiple ways. One way is to use the method of substitution, or you can use the method of elimination. I'm going to just use elimination. I'm going to multiply equation 1 by...
Professor, I think
Yes.
3a should be -3a. Someone
Yes,
pointed
you're
it out
right.
to the
Thank
chat.
you. You're absolutely right. That should be -3a. My bad. Thank you so much. I forgot my negative right
Don't
here.
think me, think Emily.
Okay, Emily, thank you. -3a. And so you can find a value that you can multiply the first equation by, say, -8, and maybe multiply the bottom equation by 3. So I would do something like this. And then distribute. And then when I add these two equations together and then solving for A and B, and I'm not going to do this in slow motion, I'm going to let you do it because you took an algebra class sometime in a previous life. I get A is -2 and B is +1. And you can check me on that. Now, what does this mean? It means that W can be written as -2 times the first vector we were working with, plus 1 times the other vector.
Oh,
And
that's
that
cool.
is being able to write W as a linear combination of the two other vectors. And you'll do this a lot in a linear. Okay, I'm going to keep going. Let's take a look at this theorem, which gives us some more ways to have fun and play with vectors. And some of this is going to be obvious. And you might go, oh, wow, that, you know, of course. And that's okay, because some of it is obvious. Okay. So how about commutative? If you've got 3 vectors in the plane and C and D are just pure numbers, they're scalars, it doesn't matter what order you add them together, you always get the same result. Okay, fine. What about associative? So what if you were adding 3 vectors together? You can add u and v and then add w, or if you prefer, you can group the v and w and add those guys together first and then add u. Same thing. How about if you add a vector to the 0 vector? You could do that. And what do you think you end up with? The vector itself, so the 0 vector doesn't add anything to it. How about if you add a vector to its opposite, u plus negative u? You will end up with the 0 vector. What about if you multiply a vector with 2 scalars? Well, it doesn't matter what order you do it in. You could, if you wanted to, multiply the 2 scalars together first and then do your scalar multiplication with the vector. How about this? If you're adding a sum of 2 scalars together and then multiplying that with a vector, you could do it that way. That's fine. Or if you prefer, you can distribute. It doesn't matter. Both are fine. Similarly, if you're taking a scalar and multiplying it with a sum of 2 vectors, do it that way. Or if it makes it easier for you for some reason, you can distribute the scalar. And finally, and this is kind of obvious, if you multiply any vector with a 1, the scalar is a 1, you're just going to get back the vector. And this one is a little bit tricky. If you multiply a vector with the scalar of 0, you don't get the number 0. You get a vector 0. And so I better see a little arrow on top to denote the vector. Okay, we're done with the theorem. Let's move on. What about the length of a scalar multiple? This is super important, even though it may seem obvious to you. You remember that a scalar multiple either stretches or shrinks a vector. If you're trying to find the length overall of the scalar multiple, you could just find, using the magnitude, which is the sum of the squares of the components. That will work. But there's an easier way. If you already knew in advance that it was a multiple, you could just take the absolute value of whatever that multiple was, make sure it's positive because magnitudes are always positive, and then multiply that by the magnitude of your vector v. Same result. Okay, now we're going to do something that is super important all the way up through the final, and that is a unit vector pointing in the same direction as your vector. And I'm going to refer to this as unitizing the vector because my mentor, Dr. Arnie Vallone, he passed away 7 years ago, but he taught me vector calculus essentially. He would call it this. By the way, this is not in the book. So when I say, hey, unitize the vector, you'll know what I mean. It means basically take the vector and shrink it down so the magnitude is just 1 unit in length. That's all it means. Or if it's really, really tiny, stretch it a little bit so that it has a magnitude of 1 unit. Okay, so here is the deal. If you're given a non-zero vector and you need to unitize it, the unitized vector, we'll call it u, you just take your vector and you divide by its magnitude. And voila, that will unitize your vector. So that will give you whatever the original scalar component was, divided by the magnitude as the first component, and whatever the other scalar was, divided by the magnitude. So you're just distributing the scalar. So let's do an example where we unitize a vector. It's super easy, folks. You don't want to blow this on an exam because then you'll kick yourself for losing points. Okay, we got 5 more minutes and then we're going to wrap it up. Let's find a unit vector that points in the same direction as this vector, 3, -1. Okay, so how do you do that? Well, first you got to go find the magnitude because you're going to need to use that. I don't know what I just did there to help you get your unitized vector. So what is the magnitude? Using the formula, it's the square root of the sum of the squares of the components. And I know that this component is a -1, and technically I should do -1 squared, but you know that I know, and I know that you know, and you know that I know that 1 squared and -1 squared give the same result, right? So square root of 10 is the magnitude or length. So now what? Well, now it's going to be pretty easy to unitize this vector. So we're just finding a vector that's unitized, pointing in the same direction. So you're going to take your original vector and divide him by this scalar, square root of 10. And then please distribute the scalar. And here's a good thing. In my class, there's no need to rationalize the denominators. I know some of you might have had an algebra teacher that, spanked you when you left radicals in the denominator and said, hey, clean that up, I will be totally okay with it. On the other hand, if you need to go rationalize the denominators, that's fine also. So don't worry, I'll give you credit for either way. All right? So that's unitizing the vector. What about finding a unit vector that points in the opposite direction? No problem. It'll just be negative u. So you'll just take the opposite in sign for the components. There you go. Now, these last couple problems are really hard because a lot of times I won't give you the intermediate step already done. What if I just said, find a vector that points in the same direction as v, but has a magnitude that's 8 times more than v? What they're asking for here is 8v. So you'll just go 8 times the original vector, which had components 3, -1, and then you'll distribute the 8, and you'll get 24, -8. So this vector is a vector that points in the same direction as v, but the magnitude is 8 times more than v was. And remember, the magnitude of v was square root of 10. So this guy's magnitude, and you can test this by checking on your own, will be 8 times square root of 10. On the other hand, letter D, I'm not asking for the same thing as letter C, but a lot of students get confused. And they think, oh, that's just 8v again. Here, I'm asking for a vector that points in the same direction as v, but the magnitude is exactly 8 units, not 8 more than the original. So this is a little bit tricky. What you're going to do, it's a two-step problem. You're going to first unitize the vector and shrink it down so it only has 1 unit, and then hit that unitized vector with a scalar multiple of 8. So step 1 would be unitize v, but I claim we already did step 1, so we did this in part A. And then step 2, you would go 8u, and that'll give you a vector that has exactly a magnitude of 8 units. So I'm going to just multiply our unitized vector, which was 3 over square root of 10, -1 over square root of 10 with an 8, and don't forget to distribute your scalar, and your final result, there is a vector that has exactly a magnitude of 8, okay? And I think that is a really great place to quit the lecture. I'm going to stay on for a couple more minutes to answer any last minute questions, if anybody has any. And otherwise, I'll see you on Wednesday morning.